Hello, and welcome today to the presentation of Team Archer. Before we get down to business, we'd like to thank you all for coming today and for taking the time to watch our presentation. We would also like to thank Best and New London Spicer High School for hosting the 2013 Gatekeeper competition. Today, we have come to answer Best's challenge to build a better robot, to build a better CPU for Squeaky the Robot, which is what we will accomplish with our robot, Ardia. Now, what exactly is Archer Robotics, you may ask? Well, as the name, Anoka Region Christian Homeschool Engineering with Robotics would imply, we are a group of homeschoolers dedicated to building a better, stronger, and faster robot to accomplish our task. Allow us to introduce ourselves. My name is Ian Erickson, and I am the lead presenter and junior engineer at Team Archer.
I'm Parker Dahlstrom, CEO and Director of the Engineering Department.
I'm Evan Erickson, Junior Engineer.
I'm Lizzie Lofstead, Vice President of Marketing.
I'm Jacob Lofstead, Senior Engineer and Technology Specialist.
I'm Connor Dahlstrom, Junior Engineer.
Our team's diversity is an asset to our company. Ranging from 10 to 18, we have been excited to see the older members mentoring those who are younger. We believe that it is this depth in age and experience that will ensure that Archer Robotics will be a strong, reliable company for years to come. Each team member, regardless of age or experience, has shown dedication to Archer by individually investing $25 into the company. We try to be environmentally friendly and financially responsible by carpooling and using recycled materials for our booth and practice game field. Although the individual member contributions were imperative to our beginning, we soon realized we would need the support of the community to see our goals through to completion. I would like to thank our sponsors for their generous donation. We appreciate that they believed in our goal of providing a quality product for you, the customer. Here is a copy of our fundraising folder, which we passed out to local businesses. On the left, there is information about Best so that they could get to know more about the program. And on the right, there's information about Archer so that they could get to know our goal and vision. Next slide. Here's our financial spreadsheet to show you that we are a fiscally responsible team. To share our enthusiasm for the BEST program, we held an open house. Our advertising on homeschool websites, as well as emails to local public and private schools, and word of mouth, family and friends provided us with a large audience. We use this time to show our booth and robot, as well as technology we have learned, such as CAD and website designer. Through this event, we recruited 4 new members who are with Archer Robotics for this season. We found that there was interest in beginning another team in the Twin Cities area. We met with the mentor and told him more about the program, and soon he had gathered enough students and mentors to start a new team. We are proud to say that Servotech is here today, competing as a rookie team.
Team organization is an important part of any company. Thus, we began organizing as soon as we knew we were going to have a challenge. We first elected a CEO to oversee the company. This person would make sure all tasks were completed in time. We then also chose leaders of the individual departments, engineering and marketing, similar to the CEO, but specialized in their respective departments. Individuals were also assigned to the different sections of the BEST Award: notebook, booth, spirit and sportsmanship, presentation. These individuals made sure that we would have a well-run company. We have learned through the past that the engineering process is a great tool to use in order to effectively build an efficient robot. We began with immediately after receiving the specifications of our challenge from BEST by defining the problems. We sat down and wrote all the different problems we would have to overcome. Next slide, please. We then brainstormed on various solutions to the problems. Any solution that came up was written down, whether perfect or not so perfect, as even the most unorthodox of ideas can lead to a game-winning solution. We eventually developed a basic plan for our robot. We had a flat base, a large flat base on which our robot, which would be in the basic form of an arm, was mounted. Our large base size allows it to remain stabilized when sitting on a table, such as this. At the end of our arm would be some sort of a gripper in order to manipulate the various items. The first thing we developed was a way to turn.
When we were contemplating how to make a robot turn, there are two ideas floating around that could solve for this. The first one was not favored that highly because it would not be that efficient. That idea was that of use of a rubber wheel attached to a motor. The reason this would not work is that the rubber wheel still had potential to slip and thus would not give us the results we wanted. The most efficient way we thought of was the use of gears. And this is a basic outline of the design for our turning system. We have a motor, which is attached to a smaller gear, which then runs against the teeth of a larger gear, and since our robot is attached to this gear, the robot will turn around with it. There is a major problem that can arise when producing gears, and this is one of the main cons that we saw. It's just one of these little teeth on a gear is just a slight bit wrong. You might as well have not made it, because it is useless. However, one of our teammates had access to what is called a shopbot, which is basically a router that's controlled by a computer program so that it is as precise as can be, and we can set it to whatever format we want. And after we got the gears cut out of polypropylene, this is the design we ended up mounting it on. As you can see here, we have our motor attached by the metal motor mount to the wooden board on which our battery and cortex are also mounted. Mounted onto this motor is our smaller gear, which, as the teeth move, they run in between the teeth of the large gear, which, as you can see, will cause the robot to turn with it, thus giving us the most efficient form of turning motion we could make.
Now for the base, there was a lot of ideas we had, but two showed to be the biggest potential. One was a plywood box, and two was a 3/4-inch PVC frame. To choose between them, we had to look at the pros and cons. The plywood box, it was easy to mount to the turntable, but it had weak joints and was difficult to make. The 3/4-inch PVC tube, on the other hand, had strong joints and was easy to make, but it was hard to mount to the turntable. We decided to go with the 3/4-inch PVC frame because the pros outweighed all the cons, and the cons were easily worked around. We also decided to put a battery and cortex onto the base, but since we chose the 3/4-inch PVC frame design, this would be difficult. So we attached a piece of wood to two of the posts, which would not only hold the battery and the cortex, but also a small motor for use for turning, as mentioned earlier. Now for prototyping. Next slide. No, back. Okay. For prototyping, we just make sure we got the geometry right, and that there's no wacky angles. For constructing, we cut plugs to connect the elbows and T's, and we cut 3/4 PVC tubes to make the individual posts. We also made a few special things, like a hole to hold a tool, so we can tighten motors, and a little stub right here, so we can hold friction tape, so we can add to the gripper or any other places that need it.
To assist in reaching the scoring locations of this game, we designed an arm with 3 degrees of motion. The first, a turning motion, was discussed earlier. The second is a winch-like system that raises and lowers the arm. And the third is a sort of telescoping extension motion. For the winch system, there were many ideas. Using simple mathematics, we were able to figure out that a crane with a drum that wound up a string going over a top pulley, next slide, down affixed to the arm would be the most efficient and robust way to do it. When the motor turns, the arm gets raised by the string. The third motion was a lot more complex. The extension. The basic idea is to have a gear that engages holes drilled in the inner pipe, and so when this motor turns, it turns the belt, which goes to a smaller pulley out on the end of the arm, so we don't have so much weight and therefore more torque on the arm. And so then when the motor turns, the arm extends, allowing us to reach all of the 42 inches required to get to the farthest CPU memory. Also, we added a slat in the back of the PVC so that the gripper would not rock back and forth. We put in a machine screw in here into the slot, keeping it sturdy and reducing weight without sacrificing much strength.
Thus far, we have discussed the various motions of our arm, but we still needed a way to manipulate, transport, and place the various items. The basic format of this was to be a gripper, as it would be fairly simple to make. Now, one thing we would like to have had was to have both sides of the gripper closed together. This would make grabbing the items easier and would grab them more secure. However, if we had two separate servos controlling each side, this would double the weight on the end of our arm. Weight was something we certainly had a problem with, as when you were at full extension, even the smallest amount of weight adds a large amount of torque to the motor. We researched a way that could use one servo to close and open both sides. However, this was somewhat complicated, so eventually we decided to stick with one fixed side and another side that closed into it. This would be easier to line up, and although it wouldn't grab it quite as well, that problem could be overcome with driving practice. Now, one issue we had was when we grabbed the dowels, they would spin within our gripper, making them difficult to place correctly. So we added two curved indents into our gripper, which would close around the dowels, keeping them straight and in the same relative position to the gripper. We added two of them in order to double our operating efficiency. We were able to transport two dowels at once. Now we still needed a way to transport the hangers. Instead of grabbing them one at a time, which would take quite a while, we used a rod that we would insert into the hangers, lift them up, place them on their scoring pole, and pull them up. This way we could transport up to 5 at once, greatly increasing our speed. We mounted it on the back of the moving side of the gripper, which let it fit well when we were trying to fit in our 2-foot box, the limitations given us by BEST. Overall, this gripper has let us have a very efficient robot, and we hope to do well tomorrow.
We use many different technologies in the design and promotion of our robot. A few of these include SolidWorks 3D computer-aided design, also known as CAD, Weebly Website Designer, there's a screenshot of our website, and Microsoft Office for the writing of the notebook and promotional materials. In addition, for programming the robot, we used a programming environment called EasyC, and we used SolidWorks eDrawings program for viewing the CAD of the game field.
When BEST presented the Gatekeeper Challenge 6 weeks ago, we devoted a lot of our time and thinking towards building our robot. And I can say, with our robot Ardia, with efficient turning mechanism, arm with freedom of motion on the X, Y, and Z axis, and our all-purpose gripper, I can say that we've accomplished that and have made the best for BEST.